Howdy, everybody. I think I fixed the audio issues, so assuming it keeps working well, we'll have a cleaner video. In this one, I want to talk about how to derive the SUVAT equations, do it quick, and especially paying attention to that one where it was like, this v final or just v squared equals v naught squared plus 2a delta s, this kind of a thing. I want to show you where this and the other ones come from in a nice, clean, concise way. And in case you haven't heard it before, SUVAT, it comes from basically an acronym where when we get these equations that look like this is how I'm going to write them. Specifically, this is going to be I'll type it out here because I think it's a mouthful. Let's type out the one-dimensional kinematics equations for constant acceleration. And we can walk away some of those assumptions, but not all of them necessarily. We'll talk more about that as we get in. But that's a lot to write. It's a huge mouthful to say. And so SUVAT is a nice way of saying what that is. And where it comes from is this position s as a function of time equaling 1/2 at squared plus v naught t plus s naught, your initial position, your initial velocity, and that constant acceleration with time and time squared for your whole function describing the position. The velocity as a function of time will be just a times t plus v naught, and the a as a function of time is, of course, just that constant a. It doesn't depend on time. All of these equations, including this one over here, v squared slash v final squared to be more precise with my notation, equals v initial squared plus 2a delta s. Again, this only works for any dimension at a time, either x, y, or z, or some other tilted coordinate system, but one dimension at a time, constant acceleration. This is my notation. Most people, most textbooks are going to notate it in a slightly different way, where they're going to use s for position still. They're going to use a for your acceleration still, but the initial velocity they're going to say is u, and the final velocity can just be then v. And, this is technically v final or v at some corresponding time. When you do this, this is where those letters come from. So the S, U, V, A, and T are all of the letters that we use here. That's why they get called the SUVAT equations. So I'm going to still call them the SUVAT equations for acknowledging that history and a quick way of notating it. But I'm going to choose to use this sort of notation most of the time, unless I'm emphasizing something specific. Like this one, I'll often do something more like V initial and V final because it's around that same corresponding delta S, and the time gets washed away. So I want to derive the pieces because I think that's going to help explain why I've chosen this notation or this notation, really. But it's important to understand what they mean and how we use them. And some of that comes down to application and practice problem solving and that nuance that you only get from doing some of that. So there's only so much I can do in this quote unquote lecture here. In case you haven't seen it before, where these come from is the only real rules that link these quantities together is derivatives and integrals. So if you take the time derivative of your position, it becomes your velocity. Depending on when you're seeing this, this might be review. The derivative of your velocity with respect to time is our definition of acceleration, how it changes, and as vectors. Now, in one dimension, it works pretty cleanly where, if this is the x component, it's going to give you your x component of your velocity, and same corresponding piece here. But we'll talk more about that as we go and progress through the course. The big piece is that they're related through these derivatives, and then the opposite of that, the integrals, where if you integrate your acceleration as a function of time, you're going to get your velocity as a function of time, remembering all of the nuance from calculus. This should be a times dt. I don't know why I wrote equals there. I don't know what's going on. This is going to be that integral form where you're going to have to remember your plus c or some other condition. In this case, it's going to manifest with just this constant velocity being the plus c, whatever that initial velocity was. But in general, you have to use some sort of boundary condition to set what that constant of integration is. And we'll even see that with constant acceleration pieces for times that are shifted for piecewise kinds of things. But if you reset the time, it will be the initial velocity at the beginning of that interval, and then you have to do some sort of transformation on your time, like a t minus some sort of time offset. But again, problem solving practice will naturally bring that about. Just showing you these rules of that's where you can see, oh, we integrate this, that's where you get the a times t plus the v naught. And then the same kind of rule happens again. When you integrate your velocity as a function of time, you're going to get your position as a function of time. So that's where you get this 1/2 at squared from doing that time integral there. The time integral on this term is going to give you that v naught t, and then that plus c constant is going to give us that initial position. So these ones, as long as we understand our calculus rules and how to apply them for the algebraic representations, super clean, super easy. It's this other one that's a little bit more of a mystery where we're like, where did that come from? That seems like kind of random. Let me show you. It's going to come in from, if we say plugging in time here is going to give me some sort of corresponding final velocity for the end of that time interval. So that's sort of the notation piece here. And by an equivalent notation piece, this is going to be the final position. And I'm going to do one more little substitution over here where I'm going to subtract this to the other side to cancel it here, really to be slow and deliberate. You can do whatever you want as long as you do the same thing to both sides of the equation. On the right-hand side, they cancel. And that's why we often say that shorthand of move it to the other side. But here we've got a final minus initial, which we typically notate as a delta S. So we're already starting to see one of those pieces pop up and where it comes from through a combination of that. The other piece, when we look at these two equations, if we're looking at them together as a pair, they share time. So if I took this equation here, solved it for time, so let's do that real quick. V final minus V initial, subtracting this to the other side, so that I can then divide by the acceleration. I could, if I wanted to, encapsulate this into like a delta V. I'm not going to because of the final structure that I'm expecting to see. But the first time I would be trying this algebra, I might do something like that. But in this case, I'm going to leave it like this, where I'm solving for this time here, this technically delta time from whenever I started my clock and said that that was the initial velocity, and whenever I ended my clock and said that was the final velocity. It's just that typically our clocks start at 0, but if I was being more formal about this, all of these t's would be some sort of delta t, a time elapsed relative to where it is. But I'm going to substitute it away anyways. So I'm going to take this and I'm going to plug it in here, and I'm going to plug it in here, and I'm going to see what happens. So let's go ahead and do that. I've got 1/2 a times this whole quantity squared, so vf minus v naught. I'm going to distribute the squared up top and down below like that. And then I'm going to probably FOIL this out later. We'll see what happens. And then I'm going to do a v naught times this whole quantity. So that's going to be pretty obviously, I can do a little bit of this in my head, a vf times v naught distributed into that first term minus a v naught squared, interestingly enough, all over a, because I got a v naught times a v naught if I write that out. And if you were having trouble following that step, write it out yourself and watch that distribution and see how you get to this. A lot of that, the way you learn physics, is by seeing and trying on your own once you kind of know the step that you should take and then figuring out how that step evolves. So this is just that first step. All I did was take this, beat it into this form through algebraic substitution and then, or algebraic manipulation, and then I substituted it in. So I'm combining this system of two equations and I'm eliminating that time through this use of substitution. And now my claim is that this whole pile of garbage is going to turn into this nice, neat, pretty algebra that is easier to write down and easier to use. But how do we get there? Well, let's take it one piece at a time. I'm going to start by foiling this out right here. So I'm going to do vf squared, take a first times a first, so this times itself. If you write out what this means, it means take a copy of itself and multiply those together. And so I have to distribute this into this term if we're not confident with our algebra yet. And then I'm going to do this term. So I'm going to get a minus vf v naught. But I'm actually going to get a second one of those because when I take this term, the insides, and distribute that over there, I'm going to get a second one of those. So really, if I slow that down, I would get another minus vf v naught. And technically, you could even reverse the order of those subscripts. But multiplication has that property where it doesn't matter what order you do it in. And then we see two of the same term, so I can algebraically simplify it down to just two of them. Hooray. We'll get more and more confident and more quick at doing similar steps like that, but I want to show some of those. And then when I distribute it onto this term, the negatives are going to cancel when I do that multiplication. I'm going to get plus v naught squared. So that's what I get from that numerator when I distribute all that out. But then I've got all of this that still has to get multiplied by this kind of stuff. So I've got this 1/2 with an a in the numerator and an a squared in the denominator. And hopefully you're just chomping at the bit. You're yelling at your screen, cancel those, cancel those. Yeah, exactly. We're going to cancel those. If you want to be really formal about how you would do that, it's a times a here in the denominator, and then you can cancel one of those out. And so you're left with this 1 over 2a, but I'm actually going to distribute this 1/2 into these because of what I notice on the term that I'm trying to combine it with. So if I have this all over here, this left term, which I'll write in blue, I've got this all over 2a, and then I'm trying to add it with this stuff over here, which is vf v naught minus v naught squared all over a. And these have different denominators. But if I just take this 1/2 and distribute it into these terms, so if I have this term divided by 2, this term divided by 2, hey, that's cool, those cancel. And these also are divided by 2. Well, now these all have the same denominator, and I can kind of extend the parentheses here, and I can just say, let's add all of this, and it's all divided by a. And now, if I clean up these pieces too, we're going to notice something here that's really cool. These mixed terms, I've got one of them that's negative and one of them that's positive. So those are actually going to cancel each other out as well. And then we're almost to the point where we've got the form that we're used to. All of this again equals delta S. I can take the A and multiply it to the other side. So we're already seeing this manifest, but we're still looking for that too. And we're looking for these pieces. So looking at what I notice here, all right, if I clean this up and rewrite it, hey, this is a v naught squared, and this is also a v naught squared, but they have a different denominator. So if I just change this by not changing it, you can do whatever you want as long as you do an operation that doesn't change an operation. That's the only other rule of algebra, which is secretly derived from the first, which is you can do whatever you want as long as you do the same thing to both sides. I'm going to multiply this by a number that doesn't change it. And there's only one number you can multiply by, the number 1. But the way I'm going to do the number 1 is very particular. I'm going to multiply by 2 over 2. Because then they have a common denominator. That's what a common denominator is. I did an operation multiplying by 1 in a very particular form, so that now if I combine these two into the same fraction, so I've got v naught squared all over 2, I have 1 v naught squared positive and 2 that are negative. So this is actually just going to simplify down to 1 negative v naught squared. Again, still over 2. So I've got negative v naught squared over 2. And this is also divided by 2, so I could put them into a single fraction, or either way I want to think about it, multiply the whole equation by 2. That's where this 2 on the other side comes from that we were looking for. So we've got this 2a delta s equals vf squared minus v naught squared, or if I wanted to rearrange it, it's now one quick line of algebra to say vf squared equals 2a delta s, and then I just add this to the other side, plus v naught squared. Or rather, they choose to write it in the other order. So v naught squared plus 2a delta s. That's where your other SUVAT equation comes from. So as long as you are working in one dimension at a time and you've got a constant acceleration, you can use these equations. This one eliminates time for you because that's where it came from, right? You don't have time anymore because you used this equation to substitute into this equation here. So that's why I give this name. It doesn't really have a name. I'm going to choose to name this, and I call it the composite equation or the SUVAT composite equation because it's composed of two of the original ones. It's composed of your velocity and position SUVAT equations. Through this substitution mechanism, we clean it up, we beat it with the math hammer, we stirred the alphabet soup until it turned into this form, which is useful if you know any three of these things. If you know the initial velocity and a final velocity and a displacement, you can solve for the acceleration that corresponded to that interval. Or if you know the initial velocity, you know the acceleration, and you know your position, you can do those things. Keep in mind the signs, SIGNs, the plus or minusness of all of these pieces in your coordinate system does matter, which is kind of funky because this gets squared. So even if it's negative, it will become a positive number at this equation level. That is important and it does matter. And it does mean if you set things up incorrectly, you might find an impossibility where you're trying to take, say you're solving for this final velocity. If you're trying to take the square root of a negative number because of the math you did over here, your math is trying to tell you, hey, you probably set something up because you're asking for something that's impossible. And as we get into energetics more, we'll even find more reasons about why that might be impossible. So that's all I got for you. Hopefully this was helpful. If not, that's why we have class. That's why we have office hours. Email me and we'll go from there. Keep studying physics.